The quantum world is, well, it's just bizarre, right? It can feel like a game where the rules make absolutely no sense. But what if I told you there's a very specific rulebook, a set of just 4 core principles that actually govern everything, from particles being in 2 places at once to spooky action at a distance? Today, we're going to learn those rules.
Okay, so let's get right to the heart of it. This is the central challenge. How do you take all that quantum weirdness and, turn it into a precise mathematical framework that we can actually use to build things and make predictions? And you know what? The answer is surprisingly elegant. The entire foundation of quantum mechanics really rests on just 4 fundamental rules, or postulates. Think of them like the absolute laws of physics for this strange new game. Our goal here is to just walk through each one so you can see exactly how this quantum rulebook is written. First up, rule number 1. Before you can play any game, you have to know how to describe the players, right? This first rule tells us what a quantum object, like an electron or a photon, actually is, mathematically speaking. Now, okay, the formal definition has some pretty heavy terms. Hilbert space, state vector, but don't get bogged down in the jargon. The core idea is actually pretty straightforward. A quantum state isn't one single definite thing. It's a state vector, that thing written like psi, which is basically a list of all the possibilities for that system, all held together at the same time in a state of pure potential. And this is really where the quantum world just veers off from our everyday experience. A classical computer bit is like a light switch. It's either off, that's a 0, or it's on, that's a 1. End of story. But a quantum bit, a qubit, it can be a blend of both 0 and 1 at the exact same time. It's not a switch, it's more like a dimmer dial, a whole spectrum of possibilities. This equation right here is the perfect picture of that idea which we call superposition. It's just saying that our qubit, psi, is some amount of the state 0, represented by alpha, plus some amount of the state 1, represented by beta. You can just think of alpha and beta as telling you the odds, or the probability, of finding a 0 or a 1 when you eventually get around to looking. Okay, so we know how to describe a quantum state, but what happens to it over time? That brings us right to Rule 2, which describes the moves in our quantum game, specifically how the system changes when we're not looking. So here's the crucial part. As long as you leave it alone, a quantum system evolves in a perfectly predictable or deterministic way. This unitary transformation is just a mathematical way of saying that all the information is preserved. It's kind of like shuffling a deck of cards so perfectly that you could always unshuffle it to get right back to where you started. The state changes, but nothing is ever lost. A classic example of this is the Hadamard gate. We can start with a qubit in a definite state, say 0. We're certain it's a 0. Then we apply this unitary transformation, the Hadamard gate, and bam, what comes out is a perfect 50-50 superposition of 0 and 1. We went from total certainty to pure potential, all in one perfectly predictable and totally reversible step. But this is where the game gets really, really strange. What happens when we stop letting the system evolve on its own and we actually decide to look at it? Rule 3 governs the act of measurement, and believe me, it changes everything. This is it, the famous collapse of the wave function. The very moment you measure a quantum system, you force it to pick one of its possibilities. That beautiful, smooth, reversible evolution from Rule 2 is shattered. The act of observation is irreversible, and it fundamentally changes the system from this world of possibilities into a single, concrete reality. So let's go back to our qubit from Rule 1. It's just hanging out in that state of superposition, a mix of 0 and 1, defined by those alpha and beta values. We're about to measure it. What are we going to see? Well, the outcome is probabilistic. We'll get either a 0 or a 1, never both. And the chances are determined by those recipe ingredients from before. The math tells us the probability of getting a 0 is alpha squared, and the probability of getting a 1 is beta squared. So this chart here just visualizes those odds. The moment we look, the whole superposition is gone, and we are left with a single concrete result. So far, we've pretty much been talking about single players. But what happens when you have multiple quantum systems interacting with each other? Well, that's our final rule, the multiplayer mode of quantum mechanics. And again, the math here, the tensor product, it sounds intense, I know, but the concept it opens up is what's truly mind-blowing. This rule is what unlocks the game's most powerful and frankly most bizarre feature. It's the mathematical origin of one of quantum's most famous properties, entanglement. This here is a super famous example called a Bell state. It describes 2 qubits that are linked together. The equation is telling us that the combined system is in a superposition of both qubits being 0 or both qubits being 1. Now just think about that. If you measure the first qubit and find out it's a 0, you instantly know the second one is also a 0. Even if it's on the other side of the universe, their fates are completely intertwined. So there we have it, our 4 rules: how to describe a state, how it evolves, how we measure it, and how to combine systems. So what? Why is mastering this rulebook so incredibly important? Well, let's just recap the big takeaways. These 4 postulates are the absolute bedrock of quantum theory. They give us one unified language to describe states, predict their evolution, understand measurement, and build complex quantum algorithms. They're the whole shebang. And that brings us right to the real world. This isn't just abstract theory. When someone is designing a quantum computer or a quantum protocol isn't working right, engineers go straight back to these 4 postulates. Is the initial state wrong? Is the evolution not perfectly unitary? Is our measurement flawed? This rulebook is the ultimate diagnostic tool. So we've learned the fundamental rules of the quantum game. It's a game of probabilities, of superpositions, of these spooky instantaneous connections. The rules are strange, for sure, but they are consistent. And knowing them is the first step to harnessing their incredible power. Which leaves us with the most exciting question of all. Now that we know the rules, what incredible new games can we win with them?